Many processes do not go to completion, but only towards the so-called equilibrium. Today we are learning to quantify this equilibrium and show ways to shift it. Hello and welcome to PhysChem Basics. Our topic today, chemical equilibrium. What is the equilibrium of a chemical reaction and how can we shift it? In the last lecture we discussed the autoprotolysis of water into H+ and OH- thermodynamically and stated that this process does not have a standard affinity. That is, this process will never run, more specifically, never run to completion. It's forbidden thermodynamically by the first and the second law. In fact, the equilibrium of autoprotolysis of water lies very much to the left. We'll figure out exactly where it lies. We have discussed autoprotolysis of water thermodynamically. The three delta quantities you see here always compare the pure products to the pure reactants. They are marked by a standard symbol that looks like an exponent, but it isn't. The standard enthalpy of reaction, delta H0 of 56 kJ per mole, means the pure products are 56 kilojoules richer in energy than the pure reactant. The standard entropy of reaction, delta S0, means the pure products are 0.08 joules per Kelvin less in entropy, more ordered, than the pure reactant. The last number will be the most important one. Gibbs standard free energy, delta G0, the standard chemical drive, has a positive sign. The pure products are 80 kilojoules more unstable than the pure reactants. That means the reaction will never go to completion. We now want to see in detail how these three quantities change during the reaction. This is relatively simple for the energy. The energy, or actually the enthalpy, starts at negative 286 kilojoules for pure water and ends at negative 230 kilojoules for the products. Energy obviously goes fairly linear uphill in the energy profile, correctly speaking the enthalpy profile of our reaction. On the x-axis, the chi indicates the reaction process. Chi equals 0 mole means pure reactants. Chi equals 1 mole means 100% conversion, pure products. Alternatively, we may also specify conversion using the reaction quotient, Q sub R, which is the quotient of the product concentration and the reactant concentration. Things look a little different with entropy. First of all, we can sketch in the entropy of the pure products and reactants. We start with relatively disordered water, 70 joules per Kelvin, and end up with the less chaotic ions, negative 11 joules per Kelvin. During the reaction, there is a mixture of both reactant and products, and mixtures usually are richer in entropy than pure compounds. This means that we do not have a straight line profile, but we may have a maximum. Let's calculate delta G with the Gibbs-Helmholtz equation. Delta G0 equals delta H0 minus T times delta S0. We plug in delta H, 55.83 kilojoules, and delta S, negative 0.08 joules per Kelvin, and get a delta G of approximately plus 80 kilojoules. We will now discuss one of the most important thermodynamic plots, namely the change in Gibbs free energy during a reaction. How does instability change during a reaction? We start with the chemical potential of the reactant at negative 237 kilojoules and end up at the chemical potential of the products, negative 157 kilojoules. So there is a clear upward trend in instability. Thus, the reaction going to completion is excluded. Note that the instability does not increase linearly from the reactants to the products, but there is a small minimum. The instability decreases from the reactants to the minimum, and this means that the reaction can actually take place in this realm. The minimum has a special meaning because it actually represents equilibrium. No matter where you start on the curve, the free enthalpy can only decrease. Thermodynamics only allows the system to move downhill towards the minimum. You know from general chemistry that an equilibrium can be quantified by the law of mass action and by an equilibrium constant K. The equilibrium constant looks similar to the reaction quotient, with the difference that equilibrium concentrations C sub EQ are used here. In thermodynamics, it is also important that we stick to a convention for the quantities that describe concentration. If we consider gases, we have to use the partial pressure of the gas in bar. If we consider liquids or solids, we have to use the mole fraction X, and when we deal with solutes, we have to use the molarities in moles per liter. This means that the thermodynamic equilibrium constant for autoprotolysis of water must be formulated as follows. There are two dissolved substances in the numerator of the law of mass action, molarity of H plus and molarity of OH minus, in moles per liter. In the denominator, the concentration of liquid water must be quantified using the mole fraction. This defines the unit of the equilibrium constant, moles squared over liters squared. By the way, as we deal with almost pure water, its mole fraction will be 1 and we can omit the denominator. H plus and OH minus are about 80 kilojoules less stable than water. From the standard affinity delta G naught, we can indeed calculate the numerical value of the equilibrium constant using this equation. The curly bracket means numerical value of K sub EQ. K sub EQ equals E to the delta G naught over RT. We plug in the numbers for autoprotolysis and get a numerical value of 10 to the negative 14 for K. We previously calculated the unit of K to be moles squared over liter squared, so the equilibrium constant of water protolysis is 1 times 10 to the negative 14 moles squared over liter squared at 25 degrees Celsius. You know that the root of this equilibrium constant, 10 to the negative 7, represents the concentration of the protons in water, and from this a pH value of 7 can be calculated. In general, we can classify each process thermodynamically concerning the change in energy and change in entropy. There are 4 possible combinations for delta H and delta S, which can be plotted into the 4 quadrants of a coordinate plane. Processes in which energy and entropy are with us, that is, the energy decreases and the entropy increases, are always exergonic, can be plotted in the 2nd quadrant, and do always have a chemical drive. For example, the decomposition of ammonium nitrate. On the other hand, processes in which the energy and entropy are not with us are always energonic and are located in quadrant 4. The conversion of graphite to diamond being an example. For processes in quadrants 1 and 3, temperature is decisive. The decomposition of N2O4 into NO2 is endothermic, energy being not with us, but endotropic, entropy being with us. This means that at low temperatures, where energy has the upper hand, the reaction has no standard affinity, but at a high temperature it does. The temperature at which the sign of affinity changes is called the floor temperature. Conversely, for reactions in quadrant 3, energy is with us, but entropy is not. Since temperature fights alongside entropy, this means that there is a chemical drive at low temperatures. The equilibrium lies on the right, and there is no affinity at high temperature. Equilibrium lies to the left. At the boundary temperature, which in this case is called the sealing temperature, affinity is 0 and the equilibrium constant will be 1. As you can see, temperature has a big influence both on the Gibbs free energy, delta G naught, and on the equilibrium constant K sub EQ. Let's quantify this. With a Gibbs-Helmholtz equation, we may calculate delta G, which can be converted to an equilibrium constant using this equation. If we combine these two equations, we get the following expression. You see that the equilibrium constant does not depend on temperature in a simple way. However, we may derive a linear relationship from this equation if we plot the logarithm of the equilibrium constant against the reciprocal of the absolute temperature. And this is called Van't Hoff's plot. The so-called Van't Hoff's reaction isobar is a straight line. To evaluate a process according to Van't Hoff, we have to determine its equilibrium constant at different temperatures. In the Van't Hoff plot, temperature rises from right to left on the abscissa. The slope of the plot can be used to evaluate for the enthalpy of reaction. With endothermic reactions, the slope will be negative. With exothermic reactions, the slope will be positive. We can also use Van't Hoff's equation to convert equilibrium constant from one temperature to another. Let's use another example, the decomposition of dinitrogen tetroxide into nitrogen dioxide, to explain the principle of Le Chatelier, which is also called the principle of smallest stress. It states that if a stress is applied to an equilibrium system, the equilibrium will shift in such a direction that the effect of stress is minimized. The aforementioned equilibrium is easy to detect optically. The color tells us on which side it lies. N2O4 is a colorless gas, NO2 is a brown colored gas. The reaction from N2O4 to NO2 is endothermic, so it consumes heat. If I add heat to the system, that is rising the temperature, the equilibrium will shift in the direction in which heat is consumed, that is, to the right side. Adding of heat is one possibility to exert stress on the equilibrium. In fact, with all endothermic reactions, equilibrium shifts to the right with increasing temperature. With the process N2O4 to NO2, the volume increases. It is an endochoric process. Increasing pressure and thus offering pressure-volume work is another form of stress. The equilibrium will shift in the direction where the volume is smaller, that is, it shifts to the left. There are also reactions that are endergonic at any temperature, so they will never have an affinity. What can we do in those cases? First of all, let's illustrate those processes with a mechanical analogy. A weight that lies on the floor will never move up voluntarily at no temperature. The process of lifting up has no affinity. If we want to force this process, we have to supply energy from outside. And this energy must be supplied not as heat, not as pressure volume work, but as so-called useful work. For example, by connecting the weight to an electric motor. Such a persistent endergonic reaction is, for example, the conversion of CO2 and water into glucose and oxygen. This so-called photosynthesis only works because light energy, useful work, can be coupled into the system from the outside. Noble table salt voluntarily decomposes into sodium and chlorine. This is only possible if we couple in electrical energy, useful work, from the outside using electrolysis. There is another way to lift the weight here. We have to connect another process which has a large affinity to the persistent endergonic process. In our mechanical energy, this can be done by a linkage which moves another larger weight down from a certain height. The weight falling down is a spontaneous process, and we link this exergonic process via a poli to the first non-spontaneous lifting of the first weight. Interlinking several reactions is very common in biochemistry. The ATP to ADT reaction is an exergonic reaction with high affinity, which is often coupled to endergonic biochemical reactions. Another example is provoking the endergonic decomposition of iron oxide to iron by removing the oxygen from the equilibrium by a strongly reducing metal like aluminum or magnesium. Let's summarize. We saw that the affinity of a process has two contributions: the energetic contribution delta H and the entropic contribution delta S. Temperature always increases the contribution of entropy. The sign and magnitude of delta H and delta S and the temperature determine how large delta G naught will be. This standard Gibbs free energy delta G naught corresponds to the difference in instability of reactants and products. From delta G naught we can calculate the equilibrium constant K. The temperature dependence of the equilibrium constant is described by Van 't Hoff's equation. More information about the topic you'll find in the book and in the lecture. Thanks for watching.